Hello students, this is Professor Chalai, and in this video we're going to go over the shapes of the atomic orbitals. As always, you can follow along with our chapter 6 workbook. Now, for this video I thought, well, maybe I don't need to make a video, I can just point you read your textbook, you saw the shapes of the different atomic orbitals, you can just look at them and be like, oh yeah, that's what they look like, looks cool, and then just leave it at that, so that you have an idea of what they might look like if you happen to stumble upon them somewhere else. But where's the fun in that, right? So let's look at this model of what we've been talking about. This kind of a wave trapped in a box. That's how we started to build this idea of electrons moving as waves as is trapped in the atom. And we're gonna see how that relates to the shape and how we can sort of understand the shape from that perspective. So let's do that. You don't have to watch this video if you don't want to learn about that stuff, but I think it's cool and it gives us an appreciation of where the different shapes come from. So I'm going to draw that again, draw that box again. So let's say this is my first wave, my second wave, and my third wave, right? And the waves, the first wave was something like this, the second wave was something like this, and the third wave was something like that, right? And then you can keep going, but we don't need any more to sort of describe the shapes that we're going to look at. Okay, so because this is a wave, right, there's going to be a positive part to the wave and a negative part to the wave, right? Everything above this zero line that I drew is going to be positive, everything below is going to be negative, and if it's completely along that line at zero, the wave doesn't exist there, if you will. So I'm going to change the colors for the positive part to be blue, and the negative part to be red, just why not? So here, this is going to be the positive part of the wave, and then as it oscillates and it comes back down on the negative side, right, we're going to have a negative part to the wave. So it's positive, negative, like that. Okay, in this wave, we have a positive part here and a negative part here, right? And then as this wave oscillates, this positive part will become negative, and this negative part will become positive. And similarly, if we think about this third wave, right, we have the positive part here, positive part there, and we have a negative part here. So as this wave oscillates, that positive becomes negative, and this negative becomes positive. All right, so we talked about how when we label these, we call this n equals 1, n equals 2, n equals 3. These n values have nothing to do with the quantum numbers. In fact, let's not use n. Let's use something else. I'm going to call them D for Sabe. D1, D2, D3, those are our waves. Okay, so this means that the lowest level wave usually only takes on one sign at a time. The second level up has two different signs at a time, right? Like a positive and a negative, and that changes. The third level above that has three different parts of the wave, sorry, with two positive and a negative, or two negative and a positive. All right, so let's think about how that relates to the actual wave. Okay, well, let's look at the n equals 1, L equals 0 electronic wave, right? So this is the lowest wave for the principal quantum number, and this is also the lowest wave for the angular momentum quantum number. So for those, right, if we imagine this lowest energy wave here, which is just along this one x-axis as a three-dimensional shape, it would maybe start to look like a sphere, and it will only ever have one sign, right? So here we have a 1s orbital, just has one sign. Here they draw it as blue because maybe it's going to be positive, right? One level up, we're going to have a sign that's positive, a sign that's negative, and then there's a part in between where it's zero. It doesn't really exist, it's zero. So let's see, for a 2s orbital, right, we have a part that's positive, then a part that goes to zero, and then another part that's negative. Or it could start negative, then zero, then positive. The exact sign doesn't matter. And then for the 3s orbital, right, you start positive, you go negative, then you go back to positive with parts in between where the wave goes to zero. So that's what that's where those come from. the s orbitals that we're looking at, where L equals 0, are all going to be this spherical shape, right? They're going to be spheres, and then they're going to change sign from inside going outwards, from the nucleus going outwards. Okay, so that's for the s orbitals. Now let's shift our focus to, so here's the s orbital. So let's shift our focus to other L values. So we talked about how s orbital is just sort of one sign, at least the one s orbital, just one sign, and that we can relate directly to this lowest wave, right? It's just one sign. It could be positive when it's like up or negative when it's down. The exact value of the sign doesn't matter. It's just one sign. Now let's look at D2. So this corresponds to L equals 0 nicely. D2 for L can correspond to L equals 1, and as you can probably guess, the wave should have two different signs to it. And if you can imagine this shape in 3D, we get this shape, right? A part that's positive, a part that's negative, or we could flip signs. Now, for L equals 1, there's three different ML value, -1, 0, and +1, like we talked about. So there are going to be three different orbitals with a very similar shape. So just for simplicity, we're going to put this little dumbbell shape, as we call it, on the three different axes. Here it's on the x-axis, here it's on the z-axis, and here it's on the y-axis, but the shapes are all the same, right? There's a positive part, a negative part, and a space in between where there's nothing. And so that's how the second wave relates to the shape of the orbitals. Now, as you go to the third level up, so this might correspond to L equals 2, you might know that you might think, okay, there's three different parts to the waves. 2 positive and 1 negative, or 2 negative and 1 positive, it doesn't really matter. So let's look at L equals 2, which gives us our d orbitals. And you might think, oh, these don't look like that. But let's look at this one right here. It's exactly like that, right? There's a negative part here, a positive part there, and then another negative part right there. Sort of. I'm stretching things, but there are going to be 5 d orbitals, right? Because ML should be -2, -1, 0, +1, +2. And so there are going to be 5 different d orbitals. Typically, just think of d orbitals as having 2 positive and 2 negative regions, except for one which just has this like ring shape in the middle that looks kind of cool. And then when you get to f orbitals, right, there's 7 of them, 1, 2, 3, 4, 5, 6, 7. The shapes are all kind of crazy. Typically, you might expect 3 positive and 3 negative regions, but some of these are, you know, kind of starts to look really weird. But these are the shapes of the atomic orbitals. They're not the electrons. The electron is still a dot, or a point particle, if you will, or a particle. But these shapes sort of describe where the electron is in the atom, or how it's moving in the atom. So that's how we should think of atomic orbitals, and these are the ones that I wanted to show you so that you can recognize them. You see a sphere, think s orbital. You see a little dumbbell shape, think p orbital, or L equals 1. You see this sort of 4 clover pattern, think d orbital. You see this sort of weird 6 clover pattern, think f orbital. All right, that's it for atomic shapes. I will see you in the next lecture for electronic structure and electron configurations and all that good stuff. I'll see you then. Later.